Okay, so limit day 4 notes, video lesson, talking about infinite limits. Now we've already talked about infinite limits a little bit, so we're going to kind of explore this idea more in this lesson. So it says, consider the function f of x equals 3 over x minus 2. And here you see a graph, and right here at x equals 2, we have a vertical asymptote. Let's go ahead and draw that in. It's going to make the next part easier. This is from the graph, or we could do this on the table on our calculator. We'll practice that in a minute. It says, as x approaches 2 from the left, what is f of x approaching? Okay, so here's x approaching 2 from the left. Well, f of x is decreasing, and so we write negative infinity. And over here, as x approaches 2 from the right, we have a positive infinity. All right, now this is all stuff that you did last year in Algebra 2, and we've seen it even earlier this year. So relating this back to limits, we have the limit as x approaches 2 from the left of our function equals negative infinity. So we're bringing this idea of infinite limits back on the table. Now you may want to say does not exist. Hang on to that thought. Okay, over here, as x approaches 2 from the right, that limit is equals infinity. So it says the limit in which f of x increases or decreases without bound as x approaches c is called infinite limits. And you may be thinking, this is nothing new. And you're right. We're just kind of bringing everything together in notation and concept. It says be sure that you recognize that the equal sign in the statement does not, emphasis on the not, mean that the limit exists. On the contrary, it tells us that the limit fails to exist. So if you're thinking on the last quiz how you would have answered this D and E or does not exist, that would have been correct. So we're opening it up now, okay? It's not that there's a contradiction, it's just that we're being more specific with what we mean by this limit fails to exist, okay? So it says determine the limit of each function as x approaches 1 from the left and from the right by using the table in your calculator. Okay, so go ahead and get your calculator out, and this is going to be a good review of how to use your table. So we want to type our function in. We want to go to our table, we want our table to set at the x value that we're looking closely at, which in this whole chunk of problems is 1, and we want our increments to be really, really small. And if I go look at my table, I can see that the left-sided limit is, it looks like it's negative 10,000, but if I make my increments even smaller, and this is a good thing to bring up here. Oh, I need that to be 1 again. If I make my increments even smaller, add in another couple zeros there, I can see that it's not negative 10,000, but that it's an even larger negative number. Okay, that's because the left behavior is negative infinity and the right behavior is positive infinity. So let's record that down and let's use good limit notation. Let's not just write our two answers. Let's write the limit as x approaches 1 from the left of 1 over x minus 1, that equals negative infinity. And the limit as x approaches 1 from the right of 1 over x minus 1, that equals positive infinity. Okay, so how will that change if the x minus 1 is being squared? Alright, well we can easily modify that in our calculator by just adding on a squared here. Okay, and again, when you go back to your, if you caught that, squared. When you go back to your table, you always want to make sure you start at 1. And you probably could have predicted this, but because we're squaring, we're not dealing with negative numbers anymore. So we've got a positive infinity trend on both sides. Alright, so we have the limit. I want you to get used to writing this. A lot of times you see this. You could write f of x here. You don't have to actually write the function out. You could just write f of x, that would be okay, equals positive infinity, and get used to writing this. You're used to seeing it now, now you need to get used to writing it. The limit as x approaches 1 from the right of our function now is also positive infinity. Okay, so let's look at part C. Let's predict what would happen. It's going to be more like part A than part B. What do you think, how is it going to change my answer? Okay, hopefully you have a prediction, and we will see if you are right. So what is happening to the limit as x approaches 1 from the left? Okay, so let's go to our calculator. Let's modify our equation, putting in the negative and taking away the squared. Let's go make sure our table is set at starting at 1 again. And it looks like it's opposite of what it was in part A. On the left we have positive infinity, on the right we have negative infinity. And if you predicted that, good job. Okay, so now let's think about what the answer to part D is. Okay, so we've got this limit as x approaches 1 from the left of f of x. And it's like C in that we have a negative, but it's also like B in that there's a squared. So remember with squared we had the same behavior. This would have been like a double vertical asymptote, or an asymptote that had an even power. So it has the same trend on both sides. So I think it's probably going to be the same trend here, but the -1, what is that going to cause? Okay, so I'm going to even just throw this out. We're going to guess that this is negative infinity. Now, you might have caught this right here. Some of you might have been just waiting to tell me in class that I made a mistake. Uh-oh. Okay, well I totally erased the problem, but that's okay, because we got what we needed. I caught my mistake, so no emails or comments on my YouTube page about that mistake. Alright, and we also think that this is going to be negative infinity as well. This is a pretty good prediction, but what's a prediction if you don't check it in your calculator? So we need to go ahead and check it. We need to put that squared in. Okay, so again, start your table back over at 1, and we can see here that it is negative infinity on both sides. And we could do this with the graph as well. You don't have to use the table. It's just nice to use the table with certain problems. Okay, so now it says if f of x is approaching infinity or negative infinity as x is approaching c, and by c here they mean a number, not infinity, from the left or the right, then the line x equals c is a blank of the graph of f of x. So you should know this by now. This shouldn't be something new to learn. This should be just intuitive. This is a vertical asymptote. So we're relating this back to rationals. Why do we spend so much time on rational graphs? It's so that you can do limits. Find all vertical asymptotes of this function. Now, remember that the way you did this before is you just would factor, and as long as this term wasn't also in the numerator, which causes something else, a whole, as long as this is just a term in the denominator, you can set that equal to 0, and you can find your vertical asymptotes, x equals 1, x equals -1. Alright? You can definitely check these vertical asymptotes in your calculator using what we used on the previous problem. If I were to plug this into y1 and set my table at 1 going in really small increments, I could see that on the two sides of 1, just barely, I would either have a really large positive or a really large negative number. Same thing with -1. And we don't really need to go through that because we're very comfortable with the graph. Okay, here you're going to have to do a little bit of investigating, okay, because x squared plus 16, you'd have to factor that. Now this actually doesn't factor. This is not difference of squares. And so, okay, doesn't factor. Let's set it equal to 0 and see if there's anything. Definitely an x doesn't factor out, which you would need to check. And again, that's not a vertical asymptote. But here I get x squared equals -16, and you could have predicted that this is a dead end here. There are no real numbers that make this happen. So there are no vertical asymptotes. You can have a rational graph with no vertical asymptotes. It happens. Alright, now cotangent. This is not a rational graph, but do you remember where we had a vertical asymptote? This is basically when is this thing undefined. That's why we're looking so hard at 0 in the denominator, because that's an undefined. So you might be thinking, well, I don't remember which one's cotangent and which one's tangent. Well, think about a value you take cotangent of that you really can't. 0, right? All right, and then the period of cotangent is pi, so we'd say plus minus pi, and I want to tack an n on because I can add pi multiple times. And what I'm going to go back and do is actually erase the 0 because I don't need that. Okay, if this had been tangent, I would need the pi over 2 here, or the 90 degrees if we were doing this in degree mode. All right. Okay, what about this one? Okay, is it enough to factor the denominator and say, oh, I have 2 vertical asymptotes? No, you have to factor that numerator as well. X minus 3, x plus 5. It looked like there were 2 vertical asymptotes, but when I go through and factor and cancel, I realize that this negative 5 is not a vertical asymptote, it's a whole. So my only vertical asymptote is at x equals negative 2, and instead I have something else going on right here. I have a whole. And I have a whole at x equals negative 5, and if you wanted to find the y value, you could. It's not asking us for that, but that's what's happening there. That's why this is called a removable discontinuity, because I can remove it. A vertical asymptote, you cannot remove that discontinuity. Okay, so it says a vertical asymptote is a non-removable discontinuity, and a whole is a removable discontinuity. You can redefine the function to exist at a whole, but you cannot do that with an asymptote. Okay, so what I'm going to do here is I'm going to write a function, just a very general function. X minus a times x minus b over x minus a times x minus c. Okay, what is my vertical asymptote and what is my whole? Alright, because this cancels, we'll do that part easy, there is a whole at x equals a. And again, I don't know the y value. I'd have to plug in, you know, it would have to be in a messy expression at this point. And my only vertical asymptote is x equals c. Okay, so now let's do this with an actual problem, with numbers and everything. So I'm going to have to factor. Okay, so I have in the numerator, I have x plus 2 times x squared minus 2x plus 4. And in the denominator, I have x minus 2, x plus 2. And I can see clearly that these x plus 2's cancel. So it says determine whether the function has a vertical asymptote or a removable discontinuity at 2. Well, at 2, it's a vertical asymptote. Okay, there is a whole actually at x equals negative 2. Okay, bring your questions to class.